Have you ever stopped to think that there's a kind of hidden mathematical code all around us? I'm serious. It's a really simple, predictable pattern that pops up in the most unexpected places, from your savings account to the seating in a giant stadium. So today, we're going to crack that code together, and it all starts with a simple question.
All right, so take a look at these. A savings plan, a stack of chairs, and stadium seating. What on earth could they possibly have in common? I mean, they seem completely unrelated, right? But believe it or not, they're all built on the exact same secret blueprint.
Okay, let's start with something we can all relate to: saving money. Imagine you put exactly $100 into your account on the first day of every single month. That balance just grows in a super predictable way, doesn't it? It goes up by the exact same amount every single time.
Or what about setting up for an event? You start stacking those chairs, one on top of the other. With every new chair you add, the total height of the stack grows. And that little bit of extra height you get with each one, it's the same, every single time. Just a constant, steady increase.
And this one, you've definitely seen this before. In pretty much any big theater or stadium, each row of seats gets a little wider as you go back. The second row has a few more seats than the first, the third has a few more than the second, and on it goes. It's a clear, consistent pattern you can spot a mile away.
So what is this hidden code that connects all of these things? Well, it has a formal name. It's called an arithmetic sequence. And trust me, once you learn to spot it, you are going to start seeing it absolutely everywhere. The official definition of an arithmetic sequence is actually way simpler than it sounds. It's just a list of numbers that either goes up or goes down by the exact same amount with every single step. That's it. No tricks, no weird variables, just steady, predictable change.
And that constant amount that's added each time, that is the key to this whole thing. It's called the common difference, and we usually just represent it with the letter D. Finding this D value is everything. You can think of it as the engine that drives the entire sequence forward.
What's cool about the common difference is that it's flexible. If it's a positive number, the sequence grows, just like our savings account. But if it's a negative number, the sequence shrinks. You know, kind of like a car's value depreciating by the same amount each year. The only rule is that the size of that step never changes.
Okay, so once you figure out that common difference, you unlock what is basically a mathematical superpower, the ability to predict any term anywhere in the sequence without having to write out the whole long list. This is where things get really cool. Let's go back to our amphitheater. Imagine it's huge, like hundreds of rows. How could we possibly figure out exactly how many seats are in the 100th row without having to manually count our way back, row by tedious row? There has to be a better way.
And of course there is. This is the prediction formula. Now, it might look a little intimidating at first glance, but let's break it down. To find the value of any term, we'll call that an, you just start with the very first term, or a1. Then you add the common difference, d, over and over again. The only tricky part is figuring out how many times you add it, and it turns out it's just one less than the term's position, or n minus 1.
Let's actually walk through our theater example with this. Step 1. We need A1, the first term. Well, that's the first row, which has 26 seats. Step 2, find D, the common difference. We know each row adds 2 seats, so D is 2. Step 3, what's N? That's the term we want to find. Let's say it's the 18th row, so N is 18. Okay, step 4, let's just plug it all in. The 18th term equals 26 plus 18 minus 1 times 2. That simplifies down to 26 plus 17 times 2. So 26 plus 34 gives us our answer, 60 seats in the 18th row. No counting required.
Okay, that's pretty powerful, right? We can pinpoint any single term in a sequence. But what about the total? What if we need to know the entire seating capacity of all 18 of those rows combined? Adding them all up one by one would take forever. Luckily, there's a genius shortcut for this too.
And it comes from this fantastic story. The legend is that a teacher, wanting to keep his class busy, gave them this incredibly tedious task: add up all the numbers from 1 to 100. But one young student, the future famous mathematician Carl Friedrich Gauss, solved it almost instantly, stunning his teacher, because he saw a brilliant pattern that nobody else did.
Here's his brilliant method. First, he wrote the numbers from 1 to 100. Then, right underneath that list, he wrote it again, but backwards. And this is where the magic happens. He added the pairs vertically. 1 plus 100 is 101. 2 plus 99 is also 101. In fact, every single pair added up to the exact same number, 101. Since he had 100 of these pairs, he multiplied 100 by 101. And because he had used two lists, he simply divided that result by 2 to get the final answer. So clever.
And that incredible trick isn't just for adding numbers from 1 to 100. It gives us a universal formula for the sum of any arithmetic sequence. To find the sum, which we'll call Sn, you just take the number of terms, n, multiply it by the first term plus the last term, and then divide the whole thing by 2. It's the Gauss method, just in a tidy little package.
So let's finally solve our theater problem once and for all. We have 18 rows, so n is 18. The first row, a sub 1, has 26 seats, and we calculated that the last row, a sub 18, has 60 seats. So we just plug it into the formula. 18 times 26 plus 60, all divided by 2. That gives us a total seating capacity of 774. Simple as that.
So why does any of this matter? Because this code, this pattern of steady, additive change, is truly everywhere. This is not just some concept you learn for a math test. It's a fundamental pattern that's built into the world around us.
Seriously, think about it. Financiers use this to calculate things like loan repayments. Project managers use it to schedule tasks that progress at a steady rate. Urban planners can even use it to project population growth. It even shows up in computer science, helping to make algorithms more efficient. It is the go-to tool anytime you are dealing with steady, predictable change.
Now, it is really important to note that not every pattern is an arithmetic one. The key difference to remember is that arithmetic sequences are built on addition. This creates a steady, linear growth, a straight line if you were to graph it. Their cousins, geometric sequences, are built on multiplication, and that creates rapid exponential growth that curves upwards like a rocket. It's really the difference between taking steady steps and making explosive leaps.
So the big takeaway here is that these simple additive patterns are literally shaping our world, from our finances to our cities. And with just 2 simple formulas, you now have the tools to understand and predict them. So the real question is, now that you know how to spot this hidden code, what other patterns will you find hiding in plain sight?